In this video, I'll be showing you how to calculate the energies like potential and kinetic, or even total energy in an oscillating system or a simple harmonic system. So in this case, we're covering simple harmonic motion, a type of oscillating motion. So how do you calculate the kinetic energy? Well, the kinetic energy is 1/2 times your spring constant of the system, K. So K is in Newton meters, times the amplitude squared times the sine squared of your angular frequency times time, so times your input in this case for your kinetic energy, plus your phase shift, theta. Your potential energy, U, of your system is calculated by 1/2 Ka squared. So the first three factors are the same, times the cosine squared times angular frequency times time, plus your phase shift. Now your total energy, E, is equal to your kinetic plus potential. So actually, if you add your kinetic and potential here, Ka squared, you can factor out this beginning term here out of both of those equations to get sine squared omega t plus theta plus cosine squared omega t plus theta. Well, what happens when you have two squares of these two trig functions and you add them together? So sine squared of x plus cosine squared of x, maybe this looks more familiar, is equal to 1. It's a very, very common trig identity. So if this entire thing equals 1, technically 1/2 Ka squared times 1 is still equal to 1/2 Ka squared. So the total energy in your oscillating system is 1/2 Ka squared. Now I'll be introducing just one more formula. Your angular frequency is equal to the square root of your spring constant times over the mass. So this guy is going to be very important, especially when you're talking about simple harmonic motion. You're going to get a spring constant a lot, especially since you need the spring constant to calculate kinetic energy and your potential. Let's move on to some problems. So for this problem, we have a simple harmonic oscillator with a spring constant of 250 Newton meters. We also have the mass of the object that's oscillating with 60 kilos, and we have the total energy work done on the system. So E total throughout the entire time, kinetic plus potential, should equal 10,000 joules. No more and no less due to the law of conservation of energy. Okay, well, let's solve for part A. Well, for part A, our total energy should help us find the amplitude. So let's take a guess. What is the formula for total energy, right? The formula for total energy is 1/2 times your spring constant times amplitude squared. That's equal to your total energy in your system. But we have the total energy. We have 10,000 joules as the total energy. And we also have your spring constant, which is 250 Newton meters. Therefore, the only variable that is unknown in this problem is amplitude. So we can do a little bit of algebra, and we can find the amplitude. Once a little algebra has been done, your amplitude is equal to 8.94 meters. Standard units, of course. So that's part A, easy amplitude. Now you might be wondering, oh, where's part B? Well, I removed it because it had nothing to do with energy. So I don't want to waste your time watching this video and do something that's not related to energy. So let's solve part C. Okay, well, really part B. But let's solve part C. When the spring is half stretched, okay, I wrote out this myself, so it should be half stretched. When the spring is half stretched, what is the ratio between kinetic and potential energy? Well, we don't even need to solve for the kinetic and potential energy here in order to understand this. Well, the formula for a spring or elastic potential energy is equal to 1/2 K times the displacement squared. Well, when the spring is half stretched, that means that the displacement is equal to your amplitude divided by 2. So the amplitude of your wave, this describes the position, amplitude divided by 2 would be straight in the middle where the spring is half stretched on either side. So if this was level 0, where x is equal to 0, your half stretch is at the points between the peak and 0. So x is equal to a over 2. So let's set x equal to a over 2. 1/2 k a times a over 2 squared. But here's the thing. We can distribute everything out. So we get 1/4 times 1/2 times k times amplitude squared. Now, look what happens. 1/2 k times amplitude squared is equal to your total energy. So that means that U elastic or potential energy, in this case, since there's no, assuming there's no gravity working right now, U is equal to 1/4 times the total, let's use a different color for that, the total energy. So if your potential energy is equal to 1/4 your total energy, that means your kinetic energy is equal to 3/4 your total energy. So this is the ratios between your potential and kinetic energies for simple harmonic oscillation. 1/2 when the spring is stretched, 1/2 the amplitude. So for this problem, you have a mountain climber suspended from a nylon rope. Now, I don't know if you're a mountain climber. I have no idea how you do it. I would feel like I would be falling every single time I went on even a little, like 5 meters up on like a rock wall or like a bouldering wall. Yeah, I don't know how you guys do it, man. But yeah, so we need to find the frequency at which he bounces, given his mass, 90 kilos. So part A is solving for the frequency. Well, we can solve for the angular frequency very easily first. The angular frequency is the spring constant divided by the mass square rooted. So we just take the square root of the spring constant, which is 14,000, and your mass, which is 90 kilos. Once you do that, you should get a angular frequency of 12.47 radians per second. So angular frequency has a relationship with regular frequency. Well, remember that regular frequency is 1 over t. So we can actually solve for t based on the angular frequency. So the formula to find angular frequency based on t, or the period of your wave, is 2 pi over t. Now we can isolate t, so we can isolate your period to get 2 pi over angular frequency to get your period. So if we divide 2 pi by our angular frequency, 12.47, we should get a period of 0.504 seconds. And to get the frequency, we just need to divide 1 over this. So let's actually write that separately. 1 over 0.504. That should be equal to 1.99 hertz, which is the unit for frequency. Okay, we have the frequency now. How much would this rope stretch to break the climber's free fall if he falls 2 meters before the rope runs out of slack? Well, how do you approach this problem? This mountain climber fell down 2 meters. So what does that tell you? Well, if he fell down 2 meters, he had some gravitational potential energy. So how do you calculate your gravitational potential energy? Mass times gravity times height. And that all turned to kinetic within these 2 meters. Not all of it, but some of it turned to kinetic energy within these 2 meters. And we can calculate that change in kinetic energy based on what your potential energy is if you set the point in which the rope is fully stretched out to be your y0 point, or your y equals 0, or ground point. So if we multiply mass, which is 90 kilos, times acceleration, or gravity, 9.8 meters per second squared, times 2 meters, we should get an accumulated energy, well, not accumulated, but we should get a kinetic energy of 17.64 joules. So this person after he falls has 17.64 joules and no more potential energy left if the point in which the rope is fully stretched is your y equals 0 point. So now that he is 1764 joules, what do you do with this? Well, this is the total amount of energy in the system. So we need to find the stretching of the rope. Well, the stretching of the rope is your amplitude in simple harmonic motion. It's your amplitude. So instead of using velocity or position or I don't even know, kinetic energy or anything like that, we can use your total energy formula. 1/2 k times amplitude squared is equal to your total energy gained. Your total energy is 1764 joules. Now we have our spring constant. We have the spring constant. The spring constant is 1/2 14,000 times amplitude squared is equal to 1764. Let's solve for the amplitude here. And once you do just the quick amount of algebra, your amplitude should equal 0.502 meters. So this nylon rope stretched quite a bit. It stretched 50 centimeters from its equilibrium point. Which I'm not sure. I'm not a rock climber, but I don't know if this is a lot. Maybe it would snap before it even reached that point. But yeah, let's move on to the next problem. So last problem. If you're hearing me say this, you're part of like the top 10% because my audience retention is terrible, and these are educational videos and they aren't entertaining at all to watch. So I get the 10% retention rate. But if you're hearing me say this, you're part of 10%. Congrats. Let's start the problem. So you have a block of mass 100 kilos and it was dropped on a spring with a spring constant of 6,900 from a height of 25 meters and attached to the spring. So if this block was not attached to the spring, then it would just bounce up and down off of the spring. But if it attaches to the spring, the block attaches to the spring, then it will create a simple harmonic motion. So it's going to allow the spring to bounce up and down, up and down. Now, what would the kinetic potential energy be of the block after 3 seconds? So we already know this is simple harmonic motion, but let's find the total energy of the system at the beginning. Well, due to the fact that the spring has no kinetic energy at the beginning, it's completely in equilibrium, and the block also is at rest, but it was dropped from a height of 100 kilos. That means the only energy in the system is caused by gravitational potential energy. So the total energy in the system is caused by gravitational, which is your mass times gravity times height. And all this should equal 24,500 joules. That means the total energy of your system is equal to 24,500. Now, in order to find your kinetic and potential energy formulas, we need 1/2 times the amplitude squared is equal to your sine squared of your angular frequency times time plus your phase shift. Now, in this problem, for simplicity's sake, we're going to completely ignore phase shift. All right? Let's just say the time starts as soon as the block hits the spring. So this is equal to your kinetic energy. And basically the only difference is that this is a cosine for your potential energy. So what do we need to find out? Well, we need to find out angular frequency. We need to find out amplitude, and that is all. Because your spring constant is given in the problem. So that is a check mark. Let's underline it with green because that usually means done. All right, let's find your total energy. Well, your total energy is equal to 1/2 k times amplitude squared. Now we have the total energy, so we can set this equation equal to that. We also have the spring constant, so we can write down the spring constant in this problem. A squared is equal to 24,500. And doing a little bit of algebra, your amplitude should be 2.66 meters. So the spring goes up and down 2.66 meters from its equilibrium position. Now that we have the amplitude, what do we find? Well, we can find your angular frequency. And the angular frequency is equal to the square root of your spring constant divided by the mass of the object. Well, we can do that. Let's go find 6,900 divided by your mass of the object, which is 100 kilos. And basically what you get is the square root of 69 in this problem, which is 8.31 radians per second. Well, great. We have angular frequency. Check. We have amplitude. And we also have the time, 3 seconds. So all we need is just plug things in. So for kinetic energy, it's 1/2 times your spring constant times your amplitude squared, which is 2.66 meters squared, times the sine squared of your angular frequency, 8.31 radians per second, times time. So 3 seconds. Now, remember, sine is the value for your kinetic energy. So the formula for your kinetic energy uses sine. So your kinetic energy, once you evaluate all this, should be 4,337 joules, approximately. And now all you need to do is find the potential energy. So the potential energy is same exact thing, basically same exact thing, but you replace the sine formula with a cosine value. So 8.31, all the same thing, blah, 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 blah. And you should get a potential energy of 20,073 joules. So, as always, now that we're nearing the end of the video, I'm going to mention OpenStax, free online textbook. I get my practice problem there. It's great. Link will be down in the description. And if you found this video helpful, consider subscribing and liking the video. I would greatly appreciate it if you did so. Thanks for watching.